Okay, so welcome to office hours recordings. So generally for this course, I talked about it a little bit just to emphasize where often the recordings are. I'm going to walk through parts of the homework to help you with the homework. And so this is homework 1, which is due in 1 week from the day I'm recording this. So 9/27. So problem 1 we went through pretty extensively last time. Problem 2 we barely touched on because we haven't covered the material for it properly. So I'm going to cover the material and then do an example that's very similar to problem number 2 in this recording. So this is our whiteboard that we have. And so here's the problem. Oh, and by the way, I'm going to try to save this whiteboard as a PDF so I can send it out, post it in the MS Teams probably. Okay, so suppose if it is sunny or not in Charlottesville, depends on the weather of the past 3 days. Show how this can be modeled as a Markov chain by displaying a diagram in transition matrix. So first, let's talk about what a Markov chain is. Really nice demonstration of a Markov chain here, and I'll put this in the chat, the link. And Markov chain is just a set of states. In this case, we have 2 states, A or B. And you could think about rainy or sunny as, or like you have a sunny state or rainy state, but really since the problem says whether it's rainy or sunny, it depends on the weather of the last 3 days. We'll have to think about not just rainy or sunny as a state, but a sequence of 3 days as a state. But we'll get to that. So think of you've got 2 states, in this case A or B, and our system, whatever system we're looking at, it's in state A now, and then it switches to B, and it repeats B a few times, and then it might switch back to A. And there's probabilities for these switches. So, I don't know, kind of fun. We can speed up. And it's random, or we're modeling it as a random system, whether it stays in the same state or whether it switches to the other state. And the way we do this, we have these probabilities of transition. So if it's in A, it's going to have some probability that it's going to stay in A. If it's in B, it's going to have some probability to stay in B or transition to A. Of course, if it's in A, it's some probability transitions to B. So this side over here, this is the probability that it's going to be in A given that it's in A. Right now, that's 0.5. So we could increase this probability. So if it's in A, it's going to stay in A 92% of the time. It's probably, oh, look, it switched over. I was going to say it's probably going to be pretty boring, but the way random things work, sometimes they switch. And the probability it's going to be if it was in A, I guess 92% is about 9 out of 10. So you would expect maybe once you have a blue one here, maybe there's a 90% chance or so that the next one's going to be blue on rainy. Now we could change these. Here's that you could see the thickness of the arrow corresponds to the probability of the switch, right? And so this on the left-hand side, this is called a, we get the same wording. It's a diagram. It's what's called here, okay, just a diagram for our Markov chain. And the piece on the right is what we call a transition matrix, right? It's this matrix right here. And it corresponds to the probabilities of making different switches. So in this system that I've set up, if it ever goes to B, it's probably not going to stay in B very long before it switches to A, and it'll stay in A for a while. We could have a switch in a system that's, let's see, just kind of playing around with these. That's much more likely to switch than stay in the same state. So as before, we'd get a lot of R's or blue. Here, we would probably see this switching back and forth a lot. And, 90% of the time it's going to switch if we go to there. So, oh, I thought this piece on the bottom was giving the order of these on here, sorry. So this Markov chain or Markov process would switch most of the time, and occasionally it would repeat. We can see. See, let's speed it up. Yeah, most of the time it switches. Okay, the way we often describe this Markov process, we describe it with a sequence. And the sequence like this is the sequence of outcomes of the system. And I guess they call it here just a pattern of rainy days or sunny days. The rainy and sunny is a classic example, right? So this is a system where if it's sunny, it's usually going to be sunny again. And if it's rainy, it's going to be rainy again. So let's let this run for a little faster. So you can see it's staying sunny, switches to rainy, it'll stay rainy for a little bit, right? Anyway, you can see the pattern here. Okay. And just as an interesting thing, the algorithm Google uses to determine the order of search results, it's called PageRank. It's a type of a Markov chain. So this is an important, powerful system. And that's, that little diagram, that little setup there is about all you need to answer this question. So let's take a look at the question. And let me think of a system where let's pick something other than rainy days and sunny days, and I'll walk through how we would do it. And all we need to do is all you need to do is write out the diagram and the transition matrix. So suppose I was watching a football game. I like football, and team can either pass or they can run. So they've got two states that they're in for a given play, P and R. They can either pass or run. Now, whether they pass or run on a given play, it depends, let's say, for example, on what they've done on the previous two plays, right? And you maybe if you like baseball, you can think about this as does a pitcher throw a fastball or a curveball? And it would depend on what his previous two pitches are, right? You don't want to if you just throw one pitch, then the other person could just sit on it. And so what we have is we've got really pass, run, and run, pass. So really, these are my 4 possible states. Right, the 4 possible sequences of 2 plays in a row and whether we've passed and run. And so let me write these as this is play number 1, and the letter after it's play number 2. So PP means they passed and then they did a pass again. PR means they passed and then they ran. So if we think about this system, right? So suppose it's PR in this state. The next state is going to, right? Suppose this is this state. The next state's going to be like here. So whatever in the previous state, the second number has to be the first spot in the next state. So this one has a P in it. So the next play, if it's a run, this would be transition to PR. And if the next play is a pass, this would be the transition to itself. If we look at this one here, it's PR. So if the next play is a run, that's a transition. Wait, sorry. The next play is a run, that would mean we transition down here because we shift, right? Whatever letter is second, that gets shifted to the left, and then we replace what's in the second slot. So pass run, the next play is a run, we go there, and pass run, if the next play is a pass, is going to be RP. So we go there. And so from the RP state, let's see where we could get from there, right? So we're going to have since it's RP, there's going to be P in the left-hand slot, and it could be an RP in the right-hand slot. So it's going to be pass. That could slant if the next play is a pass, that'll transition to up here. If the next play is a run, it would transition to PR, which is up there. And then run, if the next play is a pass, it would transition to here. If the next play is a run, it would transition to itself. So this, let me tidy up a little bit of my unnecessary things here. A little bit tidying up. And this is my Markov diagram for the Markov process. Now, what you'll have to do is you're not looking at, for the homework assignment, you're not looking at just P and R, you're looking at S and R, Sunny and Rainy, with the same idea. And instead of just taking 2 examples, you're going to have 3. Notice we can't go from, okay, so what you would have here, what I've written is sufficient for the problem. You can't do this, right? That's not allowed. There's going to be no transition that goes from pass, pass to run, run in just one play. So let me go through and put together a matrix for this. And tidying up. Guess it doesn't really matter, but okay. So let me show what a matrix would look like. We have 4 states. So get my red pen back. So there's 4 states. So it's pass, 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 run, run, pass, and run, run. So make our transition matrix. And there's no specific order. There's no right or wrong order to put these in. But whatever order I put them on the bottom, I should put the same, should use the same order up top. So pass, 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 run, run, pass, and then run, run. And what you would normally do to build this matrix, it's to describe all the transition probabilities. You would watch a football game, or maybe 20 football games, and you would look at, you'd record each time there's a pass play and then followed by a pass play. And then you would look at the next 2 plays, not, you know, you'd get rid of the first one and take the single next play. And you would look at however many times when it's a pass that there's another pass play, right? And so that would be the probability that you go from pass to pass. So that would, the number we write right here in our transition matrix would be the, where is it? The probability that you would do, that you would follow this arrow, right? From pass to itself. So let's just call this, now we don't actually have a data that we're looking at. So maybe TP, I don't know. It really doesn't matter what you call it, right? The only ones that you actually, that's worth calling out here that are special is that you can't go from pass to run, and you can't go from run to pass. So we're going to have in here, we're going to have somebody's going to tell me how to erase stuff more quickly. Let's just call it, so we can't go from pass. We can't go from pass to run. So we're going to have a 0 there. We also can't go from run to pass. We're going to have a 0 there. Pass. Okay, so if we're in this state, which is a pass, then the next play could be a run or a pass, and that could go to here or here, but we can't go from pass to run pass. So I'm going to get it 0 there. The next one, if we're here, PR, then we have to have a run in the first spot, the left-hand spot. So we could have something there and something there, but these have to be zeros. Now, if we're here at run pass, the next play, if it's a pass, then we'll be here. And if the next play is a run, we would be PR, which is here, which would leave us 0, 0. And then last, if it's run, run, it's been the last two plays. The next play is, if it's a pass, will be at run pass state here. The next play is a run, will be at run, run here, and we'll get a 0. So this matrix that I've written here would be your transition matrix, and maybe 0, 0. Maybe the subscript is the first number is your row, second is your column. So 1. So it's column 2, and then 1, 3, and 2, 0, 2, 1, and then row 3, column 2, and row 3, column 3. So on the x's, those are just going to be some numbers. They're going to have to sum to 1 in some direction because they're probabilities. Actually, they sum to 1 across the horizontal. So, but we don't need to fill in numbers. All we have to do is show that we can model this system using a Markov chain. And so what we have here is sufficient to answer this problem number 2, but you have to switch it to rainy and sunny, and you'll have to switch it to 3 days instead of just 2. So I'm going to pause the recording, and in a little bit I'll record some material for some of the other problems. And if you go into our Canvas and you go to online meetings, I'm going to name these, like right now, this is the one that we're running. It's homework 1, question 2. I'm going to have those set up, indicating which question I'll go over in each of those. Hopefully that's helpful. Thanks.
Professor.